help you recall quickly what we were looking at. Okay, so we'll resume. Can you turn on the lights, please, on the board? Thank you. So we're looking at certified deletion. Okay. So recall we looked at secret sharing, right? So we looked at the secret sharing scheme, right? Secret sharing with certified deletion. So we saw construction. We didn't prove anything, but we claimed that it works. So now what we're going to do is we're going to lift this, lift the idea to encryption with certified deletion. Okay. So the plan is that, so there are two parts to it. So the first is that I'll tell you the intuition. Okay, and then in the second part we look at the formal proof. Okay, so for the intuition, we're going to start with how one defines the scheme. So the definition of the scheme, then we look at a construction, and then we look at the proof sketch. And the proof is a bit involved, so it's good to go through the sketch first. And then in the formal proof, we'll do the same thing, but we'll do it. Actually, we can almost essentially just start with the definition. So the definition would be slightly more general than just encryptions. So we'll see why, how that's formalized, and then we look at the proof. Okay, so that's the idea. So let's call this section 1, let's call this section 2. So we'll start with section 1 now. Okay, so here's an informal definition of encryption with certified deletion. Encryption with certified deletion. Okay, so the informal definition is that it's a tuple of algorithms so we'll take all of these to be QPT algorithms or PPT algorithms. I guess all of them will be QPT except one. But okay, so there's Gen. Oh, I'm sorry, I meant it the other way. I think all of them would be PPT except one. So decrypt, delete, and verify. Okay, where these are, so this generation, do we need decryption to be? Yeah, we need verify to be classical, basically. This is the one that we care about mostly. So verify is what is classical. And this is classical in our construction. And the remaining can be quantum. And in fact, they will be in our construction. Okay. With the following syntax. Okay, so what is the syntax? The syntax is that, encrypt. Okay, so Gen, of course, is going to produce a public key and secret key. So we did not discuss public key encryption in the review. We'll do it later, but the idea is sort of clear, I guess, to most people. In symmetric key, you have the same key for both sender and receiver. In public key crypto, one party can create a pair of public and secret key and broadcast the public key. And the idea is that the public key can be used to encrypt. So anybody can encrypt, but only the person holding the secret key can decrypt. Okay, so anyone can send messages. So that's kind of the structure we're using. We don't have to. We could also use just a regular encryption scheme, but this is what is much more common, so we're going to stick with it for the moment. Okay, so that's gen. Then there's decrypt. Let's start with encrypt actually. So there's encrypt. We are going to look at encryption of a single bit, and one can generalize it to longer messages. So encryption of a single bit is VKCT. Okay, so VK is the verification key, and CT will have the following formats. It will have one part which is quantum, and one part which is classical. Okay, and everything except for this CT, everything else is going to be classical. Okay. So this is encrypt. Then there's decrypt, secret key, CT. So you take the ciphertext, it will produce the bit B, okay, that you encrypted in general. Then there's delete, which will take the ciphertext as input and produce a certificate, which we're calling V. And the verification algorithm would take as input V and the verification key and tell you whether it passed the verification or it aborts. Okay, so that's the syntax of an encryption scheme with certified deletion. And what do we want? What are the properties we want, right? So the first thing we want is that with this following syntax, okay, so this tuple, so let's call this say S, okay, S for scheme. So S is a certified or is an encryption scheme with certified deletion if so first of all, what we want is we want gen enc dec to be a valid encryption scheme, to be in this case an encryption scheme. Satisfying indistinguishability. So indistinguishable security is what we discussed last time, right? So you have two ciphertexts, you make it into a game, and then you check which one. Actually, we should shut the door. Let's take a second because we have the air conditioners running. Okay. And then, okay, so this is so in security, remember, right, from last time, we saw that if you have an encryption of 0 or an encryption of 1, the adversary should not be able to tell the difference, right? Okay, so that was the encryption scheme. Okay, so I'm not going to write the details, but it also, it has to also have correctness and all these things. So I'm assuming the encryption is well defined. So that's one property, and we also want it to be such that it holds that the trace distance between experiment 0 with security parameter lambda and experiment 1 with security parameter lambda succeeds. So the difference, the trace distance, statistical difference between them is at most 1 to the lambda. Oh, sorry, it's negligible. Why am I writing 1 to the lambda? It's negligible in lambda. Okay, and what is the experiment? The experiment is similar to what we had discussed last time, but maybe I can explain it slightly better this time. Challenger. So there's the challenger. So this is the experiment, okay? So maybe let me write it down. Where exp b is the output of the following, and since it's going to be an experiment, let me make some space on the other side and write it down. Okay, so the construction is as follows. So there's the challenger, and then there's the adversary. Okay, so the challenger produces PKSK from gen, okay, encrypts, so gets as input a bit B, right, which is in the experiment. So it runs this encryption on B and obtains a verification key and a ciphertext, right? And then this is sent to the adversary as PKCT. Okay, note that the verification key is not being sent. Okay, so this is not it's certified deletion but with private verification that the certificate was valid. So I think there are subsequent works that also make it publicly verifiable that the deletion was successful, but we are not going to look at that here. Okay, so you send PK and CT, not the verification key, to the adversary. And here there's like a nicer way of thinking about it. So you imagine that, because somebody had asked, I forget who had asked last time, or when the time before actually, when we were discussing this, a question about how do you make sure that the remaining registers that the adversary holds are actually sent to the to the challenger. And the way to think about it is that imagine that the challenger is given the algorithm for the adversary, okay, and what it does is, so the adversary in general will have some state sigma, right, that it potentially holds by itself. So you're going to put this here, and the adversary is supposed to produce a bit, a string V, which is the certificate of deletion. That's what we are trying to test in this experiment, right, whether the deletion certificate is correct. So sends the deletion certificate, but since you're controlling the algorithm, you don't know what's happening inside the algorithm, but you can give it inputs and get the outputs. Okay, so then you also take the remaining registers of the algorithm and you send it to the challenger. Okay, and then the challenger, so this is the leftover state. This is the leftover state. Okay, and then the challenger is going to do the following. It's going to run the verification algorithm using the verification key and V, okay, and check if this is 1. If it is the case, then it outputs row, or let's say else it's instructed to output perp, that the procedure failed. Okay. So we want that whether you run this procedure on b equal to 0 or b equal to 1, there should be no difference. Okay.
Can we just for a moment here, like what we mean by certificate, like some state like CT1, that's gate, and like there is C2 as well. So
yeah, this is not a certificate. This is just the encryption. This is the output of the encryption.
Sorry, ciphertext. So like
yeah,
like is that a state or like classical state or like quantum state?
Yeah. So the part that's in ket is a quantum state. This thing, if you want, you can write the whole thing as ket. Okay. So it's a classical quantum state. So it has one part which is classical, and the other which is potentially quantum.
Okay.
So it will always have this form that one part will be classical and one is quantum. That's just the correctness requirement from the definition. So we are saying that the encryption procedure should produce one part which is classical, one which is quantum. Okay, but you're right, it's not strictly needed, right? Like we didn't have to, we haven't used this in the definition anywhere yet. It will just become useful in the construction. So, but your point is valid. I mean, and nowhere in the definition have I used the fact that CT has that specific structure of a classical quantum state. What is the what? Sorry.
Sigma there. Rho and sigma.
Yeah. So sigma is any state that the adversary holds before starting the protocol, because the adversary can be arbitrary, right? It could initialize the. If you want, you could think of it as a channel and remove the input if you want. I was just thinking of it as like a big unitary and.
Why do we need to send row to challenger there?
Yeah, good point. So we discussed this last time. So okay, so let's try to understand how you would formalize certified deletion, right? So what do we want to say when we say something has been deleted? So we want to say that after the deletion has been performed, right? So suppose I'm the adversary and I send you the deletion certificate and you're convinced that the deletion is successful. What statement do you want to be able to make to formalize the idea that I have deleted the information? you would
ask your entire storage to be sent or something.
Yeah, so you're going to, so this is what is happening, right? So row is my entire storage. It's everything I held, right? So it's all my registers. And in this experiment, you're saying that if the certificate passes, right, then the storage that I had, all of that storage, is independent of whether I was initially given 0 or given 1. Okay? So that's exactly what is being formalized.
So here we are assuming adversary to be honest, right?
We are not assuming anything about the adversary. This is just a way to formalize it. Why? Because the adversary just produces the certificate V, okay? And the statement we are making is that whatever was held by the adversary is independent of whether I sent a 0 or a 1. Because rho is the entire state, right? So the definition captures that. So it's good. It's very important that you understand that the definition is actually capturing what we want, which is like one of the main parts of doing cryptography, to formalize the intuition. Any other questions?
V, is it like classical string or like a quantum state?
Sorry, he raised his hand first.
No,
Yeah.
no problem.
No, go ahead.
So are you trying to say that, like, even if the if this game's conditions are satisfied, even if the adversary doesn't send a row, because this game's condition was satisfied, we are like secure. We have certified deletion. Is it?
Yeah, because what is the game saying? I'm not saying that in practice I will have the adversary, I will ask the adversary to send some part with no. I'm just saying that in practice I will just see the deletion certificate. But the existence of this property from the game tells me that regardless of what the leftover state was, it will be independent of whether I sent an encryption of 0 or encryption of 1 after the deletion has been issued and verified. So this is just formalized. It's similar to the decrypt oracle you were asking, right, last time. That's in CCA you don't actually give access to the decrypt oracle. You're just formalizing the idea that even if they could access everything except for that, the decryption of that specific challenge ciphertext, the security is valid. Yeah.
But you would have to like in the real world, how would you like enforce this?
I'm not enforcing it in real life. I'm just in the real world I'll just get V, right?
You just get me.
Yeah. This is just making the statement that if this algorithm was running, then whatever it had left will not depend on V. That's all I'm saying. You can put the arrow here, you cannot put the arrow, it's fine, it's not really needed. Yeah. The question is really about what the adversary is capable of doing. So this is the adversary. I allowed it to do whatever it wanted. I'm just looking at one of its outputs, and using that I'm deciding something, and if the decision is correct, then I'm guaranteed that whatever else it had is independent of, statistically independent of the initial input. The bit B that was sent as an encryption. Is this clear? Yeah? Oh, sorry, you had a question, I forgot. Yeah.
Yeah, so like I just wanted to understand like what is the local operation that the adversary is performing? Like
It's arbitrary.
any arbitrary
Yeah,
channel.
yeah, it's any arbitrary channel. It just has to be efficient. Efficient because we want to make sure that, we assume that this is a valid encryption scheme, right? So we are already assuming that it's since you're doing public key encryption, right? You're assuming that it's polytime in some sense, because public key encryption you cannot do information theoretically, because you can always check all secret keys and you'll figure out which one is being used.
So from the diagram I'm just trying to understand. So after some
Yeah, but let me, no, you're right, but I should at least write it down. It holds this for all QPT adversaries. For all QPT adversaries. Okay. Yeah.
So the adversary is doing some performance based on the like public key and this ciphertext that he gets, and is outputting some state row and some classical state V. Like that is some classical output, right?
Yeah. Even if it's not the verifiable measure, so it doesn't matter.
sends that. So what does he send? Like, does he send the state as well with the quantum channel, or like what does he send? Like V or?
Yeah. So in the way I'm formalizing it, I'm asking for V and rho both to be sent. So basically, he sends everything. It just applies the quantum channel on the ciphertext public key and whatever other state he had, and whatever outputs he gets, he sends them. But the key point is that in reality, what you would do is you will only need the verification, the deletion certificate, and if the deletion certificate passes, you will be guaranteed that whatever else he has left is independent of the input B. That's what this experiment is capturing, right? So whether you output rho here or you have some other way of doing it, all you're saying is that what is the adversary capable of learning? You're just trying to make a statement about the capabilities of the adversary. That's all. Yeah. Because think about it, like if you were satisfying it, how could you possibly have any information about B, right?
What if adversary really learns something,
Mhm.
but he is just randomly giving B, so that the challenger would become a fool?
Yeah, so then the certificate won't pass, right? This is the definition. First of all, this is the definition. So you have to give me a construction that satisfies this definition, and then I'm saying assuming this definition is true, right? So you have to come up with the proper construction. Of course, if your construction is to just not check V, like if the verification procedure always outputs 1 without doing anything, obviously it doesn't satisfy the definition, right? No, maybe I misunderstood your question. Say your question again.
No, I'm saying like when the adversary sends V,
Mm-hmm.
challenger will verify with that V and tell whether he learned something or not. Right?
He will deduce whether. So this is supposed to capture whether or not the adversary correctly deleted, whether the verifier is convinced that the adversary correctly deleted what was sent to him.
We don't know how it is done, but you are saying it is done.
Yeah, so I'm saying if there is a procedure, yeah, so this is the definition, right? The definition is saying that
I think it'll be done later, like how this construction works.
the construction will appear later. Yeah. This is just saying that suppose you give me some construction, how will I know whether it actually does what it's supposed to do? So I will check this condition. I will check that if indeed your verification procedure passes, if you can prove to me that for your scheme, whichever scheme you have in mind, if the verification passes, then the remainder of the view or the remainder of the state with the adversary is independent, statistically independent of the initial B I gave. Then I'm saying I will be convinced that you have a deletion, you have an encryption scheme that does certified deletion. This is not a construction at all. Yeah.
Yeah. Then
This is just a criteria, if you like, or criterion.
Yeah, so I get it. Like, probability of B given the leftover state rho should be like same for all possible B.
Yeah. That's what is being captured. Yeah. So the density matrix that you get in that procedure, whether you encrypted B equal to 0 or B equal to 1, should be statistically indistinguishable. That's what we're clear. Because this is really capturing the state of the adversary conditioned on the verification succeeding. Yeah, so if you like, you can think of it this way. So this is like the state of the adversary, given, well, not given quite, but this is intuition. Okay, so it's not quite correct. So intuition given B was 0 and deletion certificate was valid. Let's say residual. Okay, so maybe that's the way to think about it. It should make sense.
So how do you define perp? Is that like
How do I define perp?
is that like a quantum state, or is it that you just terminate the game?
Oh, you just add, you have qubits, you can define a specific string to mean perp and a specific string to mean bot. It's just an encoding, you can choose whichever strings you like. Yeah. for example, you could add an extra qubit in everything and then just say that this qubit, if it's 0, then it's accept. If this qubit is 1, then it's something like that. I'm not giving you the low-level encoding, but that's a that's up to the convention you choose. Yeah. Yeah. Sorry, I should have clarified because we're using qubits and then there's bots and perps. So, oh, sorry, bots and truths, tops. Oh yeah, bots and tops. Okay. Anything else? Is it okay? Is the definition okay? Okay. Okay, very well. So let's now look at the construction. I'm trying to decide what I want to erase. Let's erase this side. Okay. So here's the construction. Okay, so suppose that you're given an encryption scheme, which is gen encdec. Okay, is any encryption scheme satisfying indistinguishability or semantic security, as it's also called sometimes. Okay. Then here's the definition. Okay, so the gen algorithm is going to be the same. So gen prime. So primes are the new ones, okay, that I'm defining. So gen prime 1 to the lambda does exactly what gen 1 to the lambda does. Okay. Then enc prime pk acting on b does the following. So this is basically motivated by the example that we had, or maybe it will come later. Yeah, let me write it down actually. It's better. Okay, so here's the procedure. So when I'm writing define, this is an algorithm. Okay, so it's not one line. So you're going to sample theta and x uniformly from 0, 1 to the lambda. So the random lambda bit strings. You define b prime to be b XORed with parity, theta equals 0 of x. Okay, so what this means is this is the construction we saw last time as well. So there's nothing nothing particularly new. The analysis is what would be new. Okay, so parity theta equal 0 basically means you look at all the locations where theta is a string, right? So you look at all the indices at which theta I is 0, and then you take those indices and you XOR the x's on those. Okay, so if you want, so parity theta equal to 0x is simply XOR over I such that theta I is 0 of xi. Okay, so that's the definition. So you're going to do this. You're going to sample these, and then you're going to set b prime to this value, and you're going to set ct, the ciphertext, to be the following. So you'll have h to the theta acting on x. So this, remember, was sequence of Hadamard's, right? It's tensor product of Hadamard's. So h to the theta x was h to the theta 0 dot 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 h to the theta lambda acting on x, maybe it's 1 actually, x1 to x lambda, right? So that's h to the theta x. And now, so here's the new part. So the new part is we're going to use the old encryption scheme here to encrypt this b prime. Okay. So remember, in the secret sharing, if you recall, one party was getting the quantum state, right, and the other party was getting b prime. Now what we're doing is we're giving both of these to the same party, except that one message is encrypted and the other is in the clear. Okay? Does that make sense? I'll drink some water. Okay, so the intuition is that the so we assume that this adversary at this point, right, was QPT, and the whole point was that while the adversary is QPT, it has to produce the deletion certificate, right? Because if the adversary was not QPT, they could already break the encryption, right? So then there's obviously no way they can delete it. So it was crucial that when they produce the certificate, they were QPT, but then when they're producing the certificate, if they're QPT, they cannot really see B prime, right? So intuitively, it's almost simulating the fact that there are two different provers, and this one is the prover that was supposed to produce the deletion certificate in secret sharing. Sorry, the two different parties, right? There were two parties. One party held this part, the other party held B prime, and the deletion certificate was produced by the party holding the quantum state, right? So it's essentially simulating the same thing, that so now whoever gets the encryption will only have the ability to produce the deletion certificate, but not have the other part. Okay. I don't know if what I'm saying is mind-numbingly obvious, or if it's going too slow, tell me, okay? Because I can't tell. You guys are very poker-like faces. It's a bit difficult. Okay. Where did I keep my chalk? Oh. Okay, good. So you have this. Then Vk is theta comma x. So this is the verification key. Verification key consists in the theta and x, so the basis and the encoding. Okay, so that's encryption, and you're supposed to return. So you return Vk and the ciphertext, right? Okay. Then you have decryption prime Sk acting on the ciphertext. So this does what? It passes Ct as psi comma s, and it returns x tilde. Oh shoot, did I mess up? No, I messed up. Okay, sorry. So decrypt is intuitive, right? I'll maybe not write it because, maybe let me not write decrypt. This is intuitive, right? Because decrypt, you get access to the secret key for this encryption, right? You can remove the encryption, correct? And then once you've removed the encryption, oh shoot, I forgot. There also has to be a theta comma b prime. Sorry, I forgot. You also have to send theta, right? So remember, otherwise you can't decrypt. sorry. So you send theta and b prime both, okay? So when you get the secret key, you can learn theta. From the theta, you can learn x. And then from the x, you can remove this XOR, because you know theta and x. Okay. So decrypt, I'm not going to write. So this is, let's say, implicit. It'll be in the notes, so you don't have to worry. Okay. So now here's the deletion certificate. So the deletion certificate was just that you pass the ciphertext, pass Ct as some quantum state, comma some classical string s, okay, and you return x tilde, which is the measurement. So you measure psi in Hadamard. Okay, so that's all you do. That's the deletion. And okay, and then the verification certificate is, do I write it here? We can write it here. So verification is the following. So you have the verification key, and you're given the certificate. So let's call it cert, which will probably be V when we do it, but yeah, let's just call it V. Okay, so this is, you check V matches X for all I such that theta I is 1, right? Because theta equal to 0 was already standard basis measurement that you did to XOR, and theta equal to 1 are the ones you want to check that it actually matches.
Can you just explain again, like what is implicit and like what is S, like ciphertext equal to function, like pairs?
Do you know the word pass?
No.
Okay, so the word pass basically means that, you know, like suppose you're given a sequence of 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then you can, let's just do this, right? You can pass it as a 2 cross 2 matrix. So what that would mean is that, you know, you have some convention for how you will view this string as a matrix. Okay, so the word passing basically just means that whatever input you're getting, you're viewing it as one part being quantum and the other part being classical, which is consistent with the encryption scheme, right? Because the encryption scheme is supposed to produce a quantum state and a classical string. So you're just passing it, you're assuming that it will have that syntax, and then you're processing it accordingly. That's all. Okay, so in general, you would have some ciphertext. It will have a classical part and a quantum part. The quantum part I'm calling psi, and the classical part I'm calling S.
Okay.
Okay, so maybe I can write it. This is a string. Because you don't know, right? You don't know what you don't know what state you're going to get, right? Because I have to define the algorithm in general. So I'm just saying whatever state you get, you understand it as having these two parts, and then you process the classical part. Is that clear?
So basically, like when we say like classical quantum state, so the classical part is some like orthogonal state.
Yeah,
like
yeah.
some other state, right?
Yeah, there's nothing deep. You can also consider this as making a measurement on the part that you're thinking is classical. So even if the state is not of that form, you can always measure the classical part in the computational basis and just pretend that it was classical all along.
Okay.
Do you measure psi in Hadamard where like S of I is 0, like where that bit is like 1 or something?
I'm measuring psi, all of psi in Hadamard. I'm not. Yeah, it's not. It's neglecting the part which is classical. It's just measuring the quantum part. Because remember, right? There was Alice and Bob, right? So Bob had this part without the encryption, and when Alice had to issue a deletion certificate, she would just measure her state in the.
Or it's just some dummy placeholder?
You're just passing it. I mean, it's not. Yeah, you can't remove it. It's not being used non-trivially. You're right. But you have to write it because you have to say what part you're supposed to measure, right? Yeah, you could, if you like label it properly, like if you write, I don't know, 1 to n and then n plus 1 to whatever registers, then the first n registers is what you're measuring. That's all it's saying. Nothing very deep. Is that okay? Okay, good. Okay. All right, nice. So now we can actually discuss the idea behind the security proof. Yeah, so the first thing we're going to do now is to maybe rewrite the game, but using the encryption scheme that we had, okay? So it's going to be essentially the same thing, except I'll replace the encryption and decryptions here. So let's write it down properly. Okay, so also this is, so now we are on this part where we're looking at the idea behind the proof. Can you actually read it properly? Anyway, it's nothing very critical, just the heading. Okay. So yeah, so step 0 is that we're going to write down there'll be a bunch of steps. So this is step 0, is the security game using our definition, our construction. Security game. Okay, so how does it work? So you start, so we define experiment, earlier we called the whole thing experiment. Now this is going to be experiment, we'll continue calling it experiment, but for our scheme, and the construction is as follows. So you sample x and theta. So you sample the keys for so gen here, remember, refers to maybe we can just put primes here. Okay. So there's no confusion. Okay, so the encryption scheme with deletion is given with primes, and the encryption scheme, the default underlying encryption scheme is unprimed. And so we're going to take the unprimed scheme to gen, okay, and we're going to sample x and theta, right, from 0, 1 lambda, as was there in the encryption step, right? So here to encrypt, we needed to sample theta and x, so that's what I'm doing explicitly over there. And then we're going to write b prime as b XOR parity, theta equal to 0x, right? So this is the same as over there. And now we're going to send the public key together with x sub theta. Okay, so x sub theta is shorthand for this state. So this in the paper they also use this notation, x sub theta. It's a bit overloaded, but kind of makes things a little easier and cleaner to write. Okay, so you send this together with the encryption of theta and p prime. Correct? So that's what the initial game was, right? That you send the public key and the ciphertext. Yeah. Did I mess up already? Okay.
I have more general question. So like the point of certified deletion is that you have some information and you want to give it to someone else, and now they also have this information but they can't use it directly, and the case in which they don't use it, you can ask them to delete it and then you can verify that they've deleted it. But the case in which they do use that information, then you cannot do anything, right? Then you can't verify.
Yeah, so okay.
In the sense, once you give them the secret key, they extract B. And
then of course you can't delete. Yeah.
So everything is like such that the other person has this information, and if they choose to use it, then they can. But then after that, nothing holds.
Yeah, if they use it, then of course, yeah, then it's just classical strings, right? Then there's no way you can delete it.
So they can't do anything else with the ciphertext, right?
They could, right? So there are a few very nice examples actually. I probably should have done the applications properly to motivate it. So one example was the one that I was saying at the very beginning. Right? So imagine that you write a will, okay, and you know that you're going to reveal the secret key at some point, right? So in the meantime, if you have 5 different wills, you want them to delete all the other ones except for the last one you sent, so that once they get the secret key, they can no longer, even if they are, even if they have access to the secret key, they cannot learn anything. So this is a much stronger notion. This is not just saying that you have access to the secret key. It's saying even if you're unbounded, then you cannot do it. So that security is weaker, right? Because you're assuming you're still bounded, just that you get the key, the secret key later. In this security, you're doing something even stronger. You're saying even if you're unbounded, which means you could have found the secret key yourself, right? You know this, right? In public key encryption, yeah, maybe okay. I'll take a note and I'll write you a little exercise for this. I didn't bring my pencils, did I? Yeah. So the statement is that in public key encryption, you can, if the parties are unbounded, then you cannot have public key encryption, because information theoretically, right, if you produce yeah, maybe let's do the discussion later, but the idea is you can always check one by one all secret keys, because you're unbounded, right? So you can check all secret keys and one of them will work, and you know that, and you also have the public key, so you can encrypt X using the public key, get some ciphertext, and then you know the decryption algorithm, you check one by one all possible secret keys, and eventually one of them will give you the same message back. So you can do it for a bunch of messages, then you're convinced what the secret key is, and then you can learn anything. So this definition is stronger than the one where the key is leaked later.
And that is the similar thing that you talked about, like ciphertext attack, something like that. But like here we have the access to the public key, but like kind of similar, like where we just try all the different secret key.
How is it related to the ciphertext attack?
I mean, I have the ciphertext.
Yes.
And then I try to like get the message by trying all the different keys.
Yeah. But once you have the secret key, you can recover all possible messages. In the CCA security that you're mentioning, the chosen ciphertext attack, there you could ask for decryptions of specific ciphertexts, but you could not ask for the decryption key itself, right? Because if you know the decryption key, then you can decrypt the challenge ciphertext.
Sorry, I guess like this was like brute force.
This is essentially brute force. Yeah. Okay. Yeah, so good question. And there are also lots of other applications as well, like they use an MPC. So in MPCs, you can normally show that either one party, you can have information theoretic security for one party, but not both, something like this. Like you can have everlasting security only for one party, not for the other. But this allows you to dynamically decide who the party is. So there are other applications as well, but yeah. Okay. Should we continue? Okay, good. So this is the public key. These are the encodings, right? And then the adversary gets as input, as before. So there's some state sigma together with this input. It produces x prime and rho, right? And now, if for all I such that theta I is 1, you see that xi matches x prime sub I. Okay, so x prime is the string that is sent by the adversary as a certificate of deletion. Okay, and you check it against the x that you had chosen. So if this passes, then output rho. Else you output perp. Okay, and now the claim is the claim that we want to show, right? So want to prove. Oi, oi, oi. So the claim that we want to prove is that experiment 0 has trace distance is negligibly close. So this is just notation for negligibly close and trace distance. Okay, this is what we want to prove, right? This was the main security. Okay, so far all I've done is I've written the game, the security game, using our construction explicitly. And now we look at a bunch of hybrids. So we'll modify the game one by one, and then we'll show that it suffices to analyze the newer games. Okay, so that was the first. This was step 0. Okay. Now, okay, this is with foresight. This is in hindsight. Sorry, because I'm anticipating the proof a little bit, and which is also good. Okay, we will look at the proof in some detail. But the trouble, as I already mentioned, is that we are mixing two notions of security. Okay, so in this, what we want to do is there is this computational notion, right? So this encryption is valid only computationally, and in the end, we want to make a statistical statement. And these guarantees are very difficult to. So normally, what you do is you replace this encryption with like an encryption of 0. Okay, and then you try to argue that if I did that, it won't make any difference. But the point is that here, in the end, we want statistical security. And doing something like this would only give you computational security in the end. Okay, so such an approach doesn't work directly. So what we're instead going to do is we're going to delay the B dependence. Okay, so here B is being input, right? So this B is appearing in B prime. It's appearing at this step. We want to push it farther down. Okay, because the farther away it is, the easier it gets to analyze. Okay, that's just intuition. Okay, it'll not be fully clear. I'm just telling you the approach they use. Okay, so the first idea is to defer the B dependence. Okay. So this is experiment 1, B. So here we'll have the challenger again with B, and then there's the adversary with sigma. Okay. And the challenger is going to sample x and theta as before. Now this is the new step. Now they're going to sample a B tilde, okay, from 0, 1. So this is the new step. The rest are the same, so you have pksk from gen 1 to the lambda, and B prime is defined as B tilde XOR with parity theta equal to 0 of x, okay, and this is sent to the adversary as before. So you have x sub theta, and then you have encryption of B prime, and the adversary returns x prime in row. And now the condition is almost the same, except you're going to check an additional thing. So you're going to check if B tilde equals B. Okay, so this is the new condition that we're checking, and this earlier condition, which is for all I such that theta I equals 1, x prime I matches xi. Okay, so if both of these conditions are true, you output rho, else you output perp. Okay, and the claim that we want to make now is that the trace distance between experiment 1, 0, this is actually kind of straightforward to see, we'll also prove it properly if you like, is exactly half the trace distance between the original game. Okay, so what is happening, let's try to look at it. So here what we were doing was we were choosing a B, okay, we were computing B prime, and then we were encrypting it and sending it. Now what we are doing is we are just encrypting something random. Okay, so we just pick a random bit, not the one that we were given, we just pick a random bit, encrypt that, send it, and it's only later that we check that what we picked was correct or not. Okay, this is just for intuition building, because we'll do something more clever. This is very dumb, like it's saying you know B but you forget about it, you just flip a random coin, call it B tilde, encrypt that B tilde, send it, and in the predicate, if you happen to have guessed the correct B, you proceed as you did here. If you made the wrong guess, then you just abort. Okay, so obviously with probability half you would have made the right guess and it would be identical to that game, right? And in the remaining time your trace distance is 0, right, because you output perp. So your trace distance is just half of the original. Okay, so nothing complicated so far.
And encrypt should also take a theta, right?
Encrypt should also take a theta, yes, thank you. And that is an important point as well, because so what we've managed to do is that we've managed to remove the B dependence, right, to the end, which is what we were trying to do, right? We're trying to defer the B dependence. We can also defer the theta dependence. Okay, and how we do this is as follows. Okay, so okay, first of all note that now you know it suffices to show that this object is at most negligible, right? Because these are just half, right? So if one of them is negligible, the other is also negligible. So that's what we're going to try to do now. Okay, so that's idea 1. Okay, so idea 2 Now what we're going to do, so we want to remove the theta dependence, okay? And what we're now going to do is, it's a very common trick, it's we'll purify the experiment. Okay, so we don't have to make a choice up front. Okay, so how does it work? So this is experiment 3. I think I may have missed 1 or 2. The numbering is a little wrong. Okay, I'm calling this experiment 3 for some reason. I forgot to. Okay, so here's how it works. You have the challenger, you have the adversary. Okay, so you have the secret key, you have the public key. This is the same from gen. So here's the new part. So you have 0, 0 plus 1, 1 by root 2 on systems AI BI I in lambda. Okay, so you have 2 lambda qubits, and on AI BI you're producing, on each AI BI you're producing a Bell state. Okay, so that's the new step here. And now okay, nice. Okay, and then now you sample B prime also at random. Okay, so earlier we were computing B prime using B tilde. Now you just sample B prime uniformly at random. And then of course, and also theta, you sample uniformly at random. Okay, this is the same as it was here. We just don't have X now. We'll see also we can, this allows us to push the theta dependence later. So you have PK, okay, now you send register B, okay. So you had these lambda mini EPR states or Bell states, and you sent 1/2 of the registers together with the encryption of theta and B prime. B prime again is random, okay. Again the adversary does its thing, sends you the X prime and rho. Okay. And now what you're going to do is, now you will measure A prime. Sorry, now you will measure A in basis theta to obtain xi. Right, so we're using the property that 0, 0 plus 1, 1 is essentially the same as plus, 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 minus, minus, right? Like you can write it in whichever basis you want it, it's okay. So basically whether or not you're going to use the Hadamard or standard basis, you didn't have to decide it in advance. You just measure this qubit in standard or Hadamard, and then the other one would have become plus, minus, or 0, 1. Okay, and it will tell you what the encoding is. So you just purify the procedure. Okay, and then you compute. And now you compute B tilde as B prime XORed with the parity theta equal to 0 of x. Okay. And so now this B tilde is playing the same role as the B tilde we chose here. Okay, so what we did was we chose B tilde and then we encrypted it as follows. Now what we are doing is we are flipping it on its head. We are letting B prime be completely random. Okay. And then because the choice of x and theta was not done already, it is done at this point, right, when you measure A in the theta basis. Then when you XOR, you are essentially producing this relation. Okay, so as far as the adversary is concerned, it's identical. The adversary cannot tell the difference. Okay. Okay, and then if B tilde equals B, you abort. Oh, sorry, not equals. And then otherwise, you proceed as the initial game. So if for all I, such that theta I is 1, xi have to match x prime I. If this happens, oh yeah, this whole thing is else, right? Then rho else else abort. Okay, eliminate. Yeah, sorry, it got a little bit messy, but I hope it's clear. Okay, so now you're doing exactly the same thing, right, as you did over there. So you're checking if b tilde equals b, and yeah, it is exactly the same thing. Sorry, I kind of messed up. I didn't have to write it. Okay, so the check is exactly the same. Okay, and now here the claim is that, so now the claim is that it suffices to show that trace distance between experiment 3, 0 and experiment 3, 1 is negligible. Okay, because the trace distance between the game 1, right, and game 3 is the same, because the adversary cannot tell the difference. It's exactly the same thing as far as the adversary is concerned. Okay.
So from experiment 1 to we made the change, like we removed x by introducing Maxwellian diamond state.
From 1 to 3, you mean? Sorry, because sorry.
Yeah. But then you also changed like b prime. Like, did you change two things or?
Yeah, I had to compensate, right? Because I don't know what x is, right? In the beginning, I don't know what x is. So I don't know how to compute b prime. So what I do is I'm deferring the two things, and in the end, I'm choosing this such that everything matches. Yeah, yeah. Okay, so these things look very simple, but coming up with them is very, very difficult. So that's why this intermediate step. Otherwise, you could directly go here. You could try to see that it's the same as the first, but it just helps having a few extra steps. Okay, and we'll prove all of this. I'm just saying things now, but we'll prove it properly at some point. Okay, so this is fine.
Can you just explain the notation, the bell state on AI, BI? I mean, I don't.
Yeah, so recall that so we said, right, that we will define registers. Yeah, it's just saying this. It's just this state. So it's 0, 0 plus 1, 1. I'm not writing the normalization. Okay, let's write the normalization. So this is A1, B1. Then, 0, 0 plus 1, 1. On A2, B2, and so on. Okay. A lambda, B lambda. That's all it's saying. Okay, and then you send all the B registers here instead of. So you keep the A registers to yourself. You send all the B registers. Okay. Yeah, and it's good. We'll use such notation often because yeah, it's kind of handy.
Still, I have
No, ask. That's the whole
like
point.
the bell state A1, B1, like what do you mean by A1, B1 is a string, right? Or
It's the name of a register. So this is
okay,
A1.
so the Hilbert space is like A1 and B1.
Yeah. Remember from the initial lectures, we said that there will be physical systems A, and then the Hilbert space would be associated with this, and then we'll write everything in the vector space. So a register is basically referring to the physical system. So think of it as a silver atom. So so A1 is a silver atom, B1 is a silver atom, A2 is a silver atom, B2 is a silver atom, and so on.
Yeah, so like first one is like bell pair between like A1 and B1.
Yeah.
Okay.
Yeah.
I got it.
Yeah, exactly.
Then you send the B.
Yeah, all the B's.
String
Yeah.
of B's.
Not the string of B's. You send all the silver atoms which were labeled by B. Yeah.
Okay.
Okay. Good. Makes sense. All right. Right. So this is what we want to prove now. Okay. Okay, and experiment 4, which I'll actually not write down. Maybe I can just write it like this. Okay, so experiment 4 is going to be, how much time do we have? We have, it's until 11:25.
14 minutes.
Okay. Okay, good. So now the last step is going to be the following. So the last step is a very simple and obvious observation, which is that one can move this theta because it's not being used anywhere, right? In the previous steps you needed theta because you were using it to compute b prime, which had to be sent. But since now b prime is being sampled uniformly at random, right? You're not really using theta to send this message, which means you can move this theta dependence to after you receive the response from the adversary. Okay, so you've managed to move everything to the very last step. So you've managed to move the b dependence to the last step here, right, in the decision, and you've managed to move the theta dependence as well because you check it over here, you compute theta at this point. Okay.
So in this case, you'll encrypt without the theta also.
Oh, did I mess up? No, you're right. You're right. And this thing is set to 0. Thank you. Thank you. Yeah. So b prime we already did not. Yeah. So b prime we were using theta and we were sending theta. And now the important thing that he mentioned, which actually I missed, thank you for spotting it, is that b prime is independent of theta, that's fine, but still you needed theta because you were sending it. But now you just send 0 to the k, okay? And this is what we'll call experiment B4, okay? All right. Okay, so now there's going to be a lot of talking because the actual proof we'll do next time. So I'll just tell you the intuition for how the final argument goes. Okay, so the key thing is that it turns out that using prior tools, that we'll look at these tools, once you've removed the theta dependence entirely from here, right, you're only sending 0 to the k, and there's no b dependence, okay? So the adversary is actually not getting b at all, right, as far as and it's not getting theta either. So it's getting no information at all about theta and b. And then we can essentially use the ideas from prior things to argue that the adversary will not be able to, the view would be independent of, statistically independent of b, okay? Because the main difficulty was that this part of the analysis was computational. We've removed that now in experiment 4. Okay, so in experiment 4 there is no need of this because this is just sending some junk information to the adversary. So this is relatively easy to analyze and one can show that we can indeed satisfy our definition. The difficult part is showing that experiment 3 and 4 actually are the same. Okay.
3 and 4 is that you send theta to the end.
Yeah, so 4 is you send theta to the end and you send 0 to the k, I wrote 0 to the lambda instead of instead of sending theta. So basically you remove theta dependence, yeah, push it to the end, exactly.
Aren't they already equal?
They would be if you were not interested in statistical indistinguishability. What you're saying would have been correct if in the end, everyone was computationally bounded somehow. But what we want is statistical indistinguishability.
But in 3, already we're not using anything from theta. So
We are, right? Theta is being sent.
isn't it 0 to the k?
In 4.
In 4.
It's 0 to the k.
Yeah. 0 to the lambda actually, sorry. There's no, k and lambda are the same. I mess up. Yeah. That was the important thing he mentioned, which I kind of forgot to state. Yeah. Okay. So the intuition for 4 is so it's relatively easy to show that 4, the trace distance between experiment 0 of 4 and experiment 1 of 4 is negligible. That is relatively straightforward. We'll see. But the main difficulty is in showing that 3 and 4 are the same. And the way that is shown is by using what they call an efficiently checkable predicate. Okay. So we look at this next time. The efficiently checkable predicate is almost the same as the verification condition that we check here. Okay, we'll see. So there's an efficiently checkable predicate, and identifying this is normally not that straightforward, I guess. Predicate. And what this allows you to do is that on the state of the challenger, it's able to so on the state of the challenger, you're able to, from the state of the challenger, you're able to apply this predicate. A predicate is something that sends you to 0, 1, right? It takes some input and sends you to 0, 1. So from that, you can construct a predicate which is efficient. So you can compute it from the challenger of experiment 4 and the challenger of experiment 3. And you can argue that this efficiently checkable predicate must behave the same in both experiment 3 and 4, because if it does not, then you can break the security. Okay, so instead of using like the final step to do the indistinguishability, you have to construct some predicate which uses some the state of the challenger in some intermediate step, produce some predicate, and then show indistinguishability, saying that if the predicates were different, then you could do the you break the encryption, and if the predicate is satisfied, then you can continue analyzing as you analyzed experiment 4. So that's kind of the high level idea. Okay, and we have about 6 minutes, right? So I can actually start with the preliminaries for the actual formal proof.
Why did we go from this experiment to that experiment?
Sorry, say it again. Why? Oh, because the primary difficulty is that in the end you want statistical security, and this is only computationally secure. So all the tools that you learn in crypto when you're doing computational security is just works with computational security. Here you're mixing both. You're mixing computational security with information theoretic security. So any statement that you make about, because remember the indistinguishability games, right? What do they say? They say that if I replace the ciphertext of 0 with ciphertext of 1, you cannot distinguish as long as you're computationally bounded. But here the statement becomes statistical, right? It's saying that even if you're unbounded, you should not be able to distinguish. So those techniques fail if you try to apply them directly.
There we only need statistical.
Yeah, so here what we are doing is we are trying to push everything to the very end, and that allows us to deal with all the previous steps without worrying about the encryption, because at this point you have 0 to the lambda and something random, right? So it's really not learning anything, and then from that the analysis becomes easier and you can get statistical security. So how that's done will obviously become clear once we go through the full proof.
But we are using more computation and more resources in this experiment than.
Oh, these are just security proofs. You don't actually do this in reality. In reality, you run the scheme as I said, right? You run the encryption, and then you ask for the deletion certificate. That's all. These are just constructed to show that the scheme is secure. Yeah. These are proof techniques. These are not done in the lab.
So the predicate being true for the first and third experiment doesn't imply the experiments are the same, right?
Yeah. They basically show that the probability that this, the distribution of the predicate in the first case, in experiment 3 and in experiment 4, must be the same, because if they are not, you can distinguish the two cases.
What do you mean distribution of predicate?
Like the output distributions, you evaluate the predicate. Yeah. We will look at it in more detail, and it should become clear. Okay, so we have 5 more minutes, so let's make the most of it. All right. Okay, so I'm going to define some. Okay, so this is section. Well, okay, according to the thing I'd written earlier, this is like the formal proof part. Right, so this is the formal part. So here everything should be crystal clear. Okay, no hand waving. So everything should be very precise and explicit. So we'll start with preliminaries. And yeah, I think the first few lectures when we actually start doing these things would require some effort because we are introducing lots of new concepts. But over time we'll see that the concepts sort of get easier because you have some familiarity. Okay, so lambda is the security parameter. This we know. So these are just symbols I'm writing that you can recall, right? So lambda is security parameter. Nagel we already defined last time, right? Anything less than strictly less than 1 by poly. Then we're going to use the following definition. So we'll use h of x to mean the number of non-zero entries in the string. Okay, so that's just the Hamming weight. Omega x would be the, or the w I think is probably a better word because it's weight. Weight of x is just the relative weight, so x pi, and where n is the length of. Okay, the number of length of x is number of bits in x. Okay. So now you have xy. Okay, so this is an alphabet. I don't know why they're using a general alphabet, but okay. Okay, so then we'll define the distance between x and y as the relative weight of x XOR y. Okay, it's the relative Hamming distance of the XOR of the string. So basically asking how many bits you need to flip in order to get this, to change one from one to the other. Okay, very good. Now we have quantum preliminaries. Okay, so here what do we need? Yeah, all of this stuff you know. Trace distance you know. Okay, yeah, so we'll need the standard quantum notation which you already know. We discussed at length. There's this thing called a gentle measurement. So a gentle measurement. Okay, so I guess we'll stop after defining the gentle measurement. Is as follows. So suppose that rho x is a quantum state. Okay, and pi identity minus pi is a projective measurement. On x, okay, such that trace of pi rho is greater than 1 minus delta. Okay, so you're very likely, given this rho, to obtain the answer. Let's call this 1. Okay, let's call this accept. Let's call this reject. Okay, and you define rho prime to be this object. Pi rho pi is the post measurement state. Okay. Then the statement is the following. So then you can say something about the trace distance between rho and rho prime in terms of delta. Okay. So if you're somehow guaranteed that the projector succeeds with this probability, then you know that the post-measurement state and the initial state are very close in traces. And this will be useful because as we'll see, basically we use it for the like when we do the test, measure everything in the Hadamard and we check for consistency. Using this lemma, we'll be able to say something about how close the states are given the outcome of the measurement. Okay. How close the post-measurement state is given the outcome. Okay.
Is this for any delta or only for small delta?
The theorem doesn't say small, so it's for any delta. Yeah. I mean, of course, it has to, I guess, to be at most 1, but besides that, it's okay. Okay. So it defines non-uniform quantum Turing machines, which is probably not needed. The XOR extractor. Okay. Good. So, okay. I guess it's a good time to stop. Next time we look at the XOR extractor. Okay. So that's section 2 for next time. And we'll actually start with proofs. Okay. This I'll not prove because it's a standard statement, and I also don't remember the proof. But so we'll state this XOR extractor, and we'll look at the proof next time. Okay. All right. So thank you.
What is
Oh.